your shoulders loosen and your breath ease into a slower rhythm, gentle and even. You are safe here, unhurried and unwatched, listening to a story told in a low voice about patient measurements and the tender tedium of carefully mapping a sky that is always there, always quiet, and always full of a warmth just above absolute zero. If you enjoy this peaceful journey, please tap like and subscribe, and if you would like more sleepy science to carry you through the night, a playlist link waits gently in the description, ready to play on while you drift. How sleepy are you on a scale of 1 to 10? Picture a very faint light, not a light you see with your eyes, but a glow your skin would never notice, a warmness not warm. 2. 725 degrees above absolute zero. It is the cosmic microwave background, the leftover heat from a time when the universe was so dense and bright that light did not travel far before it was scattered, nudged, and scattered again. That light has cooled with the slow expansion of space itself, stretching into longer, softer wavelengths until it became a sky-filling whisper, a hushed blanket of microwaves surrounding us everywhere, at all times. Imagine yourself under that blanket now, not pressing or heavy, just present, steady, like the quiet hum of an old fridge in the next room that you notice only when everything else is still. Scientists map that blanket, pixel by patient pixel, with telescopes that look not through a lens, but through horns and waveguides, across windows cut in the atmosphere, or from balloons and satellites that float the instruments above the damp, busy breath of the earth. The gentle rhythm continues, a slow sweep across the sky, then another and another, as the instruments learn the small differences, the tiny ripples that tell the story of the universe as a baby, long before stars and galaxies and the long delicate filaments of the cosmic web found their shape. You find yourself beside a quiet telescope in a quiet place. Perhaps you are breathing the dry, thin air of the Atacama Desert, where the wind is a steady sigh over pale gravel and the sunlight fades into a metallic blue dusk. The concrete pad under your feet cools slowly after the day's warmth, and a soft clack as metal contracts accompanies the hush. Or perhaps you are at the South Pole, where the snow smells like nothing at all, and the cold sits close to the ground like a careful guardian, keeping moisture and noise to a minimum, and making the sky into a cleaner window. The telescope moves so gently that you feel, rather than hear, the change, a slow nod from one side of the sky to the other. The gentle rhythm continues. Inside a sealed receiver, behind doors and filters and careful baffling, the detectors sit in a bath of cold, so deep that metal becomes quiet, and even the small jitter of atoms slows to a near stop. Cables make soft curves like sleeping snakes, and braided shields absorb the leftover chatter from the world, until the only sound left is the whisper of ancient light, the whisper of the universe as it was when it had barely learned to be transparent. The people who build these instruments speak softly here, Imagine yourself holding a small, calibrated light source, shining it into the telescope's throat, a calibration tone so gentle that it is like tapping a crystal glass with a fingernail. A small bump appears in the data stream, a calm peak, right where it should be. The gentle rhythm continues, then a different light at a different frequency, a scan across a quiet planet, Jupiter perhaps, or Saturn, a moving point that becomes a rounded hill in the data, revealing the beam pattern, the way the telescope's attention softens at the edges, the way nothing sees the universe perfectly, and that this imperfection can be learned and folded into understanding. You find yourself tracing lines on a sky dome map that wraps above you like a gentle tent. There are paths drawn in slow arcs, scanning patterns designed to let every detector see every point on the sky from many angles, again and again, so that slow drifts in the instrument can be separated from true features, and so that the faint weave of polarization can be found. Polarization is a special kind of whisper within a whisper, like the way light can be said to vibrate more in one direction than another, a gentle preference left by scattering in a young universe, and later by the subtle bending of space, by matter that would one day become a galaxy or a cluster of galaxies. The scanning pattern repeats and repeats again, a comfortable routine, a ritual of motion. The gentle rhythm continues. On a mountaintop, the telescope tracks at night, when the atmosphere is calm and the sun is below the horizon, the ground radiating its heat back into space in a long, slow exhale. Inside the lab, a screen shows a river of data, not as numbers, but as a pale chart with tiny variations, each tiny variation wearing the same quiet face. There are logs kept by people who know that the sky remembers everything, but the instruments must be reminded. Weather logs, with gentle notes about wind speed and humidity. Cryogenic logs, with temperatures that change by tenths of a degree over hours. Power logs, pointing logs, housekeeping logs, all telling the story of a night that is rich in detail and nearly eventless. In the morning, a sun that rose slowly sees the telescope nod to a safe position, a small stretch after a long watch. The gentle rhythm continues, day into night into day. Imagine the first maps, rough and coarse, made by a satellite named Cobe, that noticed the universe is not perfectly smooth. Those maps were like discovering that the sea, which seems flat from a distance, actually has swells and troughs that carry a memory of winds that blew even before any water you could touch was there. Later, a spacecraft called WMAP painted the sky again, with finer strokes and surer lines, and the pattern of swells and troughs gained detail. Then Planck, with eyes that saw in many colors of microwave light, made the pattern even clearer, resolving delicate variations that were hiding in the blur of earlier views. You are not under pressure to remember the names. You can let them wash over you like slow waves. What matters is the feeling of that detail sharpening, the way a patient painter adds layer after layer of thin wash, waiting each time for the previous coat to dry, until the image glows without having ever been rushed. The gentle rhythm continues. These maps tell stories through statistics, not through pictures you would hang on a wall. The pattern of variations is described not by dots and lines, but by a spectrum of gentle fluctuations, waves laid over the sky at many sizes, some large enough to cover half the dome above you, some small enough to look like tiny pepper on the pale blue of the map. This spectrum has peaks and valleys that say how the young universe rang like a bell, with gravity and pressure keeping time. The timing of those rings, the heights and widths of those peaks, reveal densities and speeds and ratios, the amount of ordinary matter, the larger amount of dark matter, the calm, persistent pressure of dark energy that urges space to expand. It is as if the universe left a lullaby for itself, one that can be read with patient eyes, and whose notes, once learned, tell you the shape and age of all things. The gentle rhythm continues. In a small, temperature-controlled room, a computer hums softly, fans whirring at a constant speed. The pipeline runs, not a metal pipeline, but a sequence of steps, code written by many hands and voices, each step named, tested and described. Time-ordered data become maps through a kind of listening that is careful to remember where the telescope was pointed, how fast it moved, and how a detector's slight laziness might smear a passing feature. Imagine those time streams as threads, dyed in slightly different shades, being woven into a quiet tapestry, the weave pattern chosen to keep stripes from forming, and to keep noisy knots from spoiling an area where the cloth should be smooth. The gentle rhythm continues as the system subtracts the slow baseline drifts, filters out the harmful breaths of the atmosphere, nods to the known global dipole signal that comes from our motion through the cosmic rest frame, and centers the data in a frame where the sky stands still. Foregrounds appear like friendly, inevitable clutter in a room you live in every day. Our own Milky Way contributes soft haze made of dust, warmed by starlight, and a diffuse glow from electrons spiraling in magnetic fields, a process called synchrotron emission. There is also a gentler, flatter glow from free electrons when they pass near ions without binding, called free emission. Each of these has a preferred color in the microwave spectrum, a way of speaking that becomes more distinct when you listen at many frequencies. Multi-frequency experiments learn to separate these voices by comparing the way the brightness changes with color in each pixel across the sky. The methods have gentle names and firm mathematics. Some find a best fit to a model of each foreground component. Some blend the maps in a way that reduces the clutter overall, and some place smooth, kind priors on what the sky is allowed to do, preventing wild swings where quiet is expected. The gentle rhythm continues as the foregrounds are tucked away, not lost, but layered aside, to leave the faint, nearly uniform glow that carries the oldest story. Polarization maps require even more patience. Light can be polarized when it scatters, and in the early universe, it scattered often, so a faint pattern of polarization, called E-modes, others might arise from gravitational waves left by inflation, the rapid expansion that smoothed the very early universe. The search for those primordial B-modes is a study in gentleness, because the signal is extremely faint, and our galaxy's dust also has polarized emission that can masquerade as the pattern being sought. The gentle rhythm continues as teams map, cross-check, subtract, and map again, allowing a quiet truth to emerge from under friendly, stubborn layers. A winterscape at the South Pole comes into view. The sky is a deep, soft blue that looks almost solid in the cold. The telescope sits on a platform that does not creak, tethered by bundled cables that arc inward toward warmth. The observers move slowly, breath-making small clouds that are whisked away by the clean air. The noise floor is low here, the atmosphere so dry that its microwave voice is nearly silent. Sleds bring supplies, and the little vehicles that ferry people around are stored carefully. Inside, the warm room smells faintly of insulation, dustless plastic wrap, and the sweet metallic note of aluminum. Coats hang heavy on a rack, hats arranged like sleeping animals. The gentle rhythm continues as a team member adjusts a set of filters, their fingers sure and calm, while a colleague marks down the exact time and the exact conditions. There are no urgent movements here, only the small, steady actions of daily care for a machine that listens to the oldest signal it can hear. Atacama night has its own softness. The wind carries a mineral whisper, and the stars seem close. A telescope here watches areas of the sky that never set, following them over and over again. When a planet rises into view, it becomes a chance to calibrate the beam, to observe the brightness profile, and make a record of the instrument's point spread function. This is a kind of portrait of the telescope's own way of seeing, learning its gentle blur, its quiet asymmetries, and even the faint side lobes that might collect unwanted light from the ground or a bright source off to the side. The gentle rhythm continues as these beam maps are fed into the pipeline, shaping the corrections that will later sharpen the view of the cosmic background, and making sure that when a small hot spot is seen in the map, it is not the instrument's own breath. Imagine again the data as a river. It is a river at night, shining with tiny reflections. The flow is measured in counts or volts or some other unit chosen and written out, and those units are carefully converted into sky temperature, anchored by the known brightness of the cosmic dipole, and by planets observed so often that they feel like old friends. The data are cut into segments where the conditions were steady, and flagged where a bird flew by, or where a small cloud added a brief gloss to the sky. Any moment of odd behavior is set aside, and the labeling is gentle, descriptive, and precise, because everything will be checked. The gentle rhythm continues. From time-ordered streams come maps on a chosen pixel grid. Perhaps the grid is a sphere divided into equal area pixels, each one a small patch of sky whose center is defined forever. The resolution might be fine or coarse, adjusted for the science at hand and the memory at hand. In the end, you can spread that map like a quilt, with colors assigned to small tiny arrows that hint at patterns you feel more than think. Now picture the power spectrum, not as an object, but as a soft outline, the way sound looks if you plot loudness against pitch. Each multipole number corresponds to a large shape in the sky, lower numbers for larger shapes, higher numbers for smaller grain. The spectrum has peaks. The first peak is a strong one, like the first tone of a chime struck with care. The second and third show themselves with a certain modesty. The positions and heights of those peaks speak of the cosmic orchestra, of how much matter moved with gravity, how much pressure pushed back, how tightly the universe was coupled, and what kind of primordial fluctuations were seeded before this ringing began. To measure the power spectrum well, you average carefully over the sky, and the way the sky is masked to exclude bright foreground regions is itself a calm art. The gentle rhythm continues as simulations are drawn up, synthetic skies that mimic the noise and scanning and imperfect beams, so that each subtle bias can be understood and folded back out, leaving a spectrum that is as honest as it can be. From those spectra, parameters emerge, not with drama, but with gradual reliability. A fraction for ordinary matter that matches the light we see in stars and gas. A larger fraction for matter that does not shine, but weighs on the dynamics of everything. A measure of the Hubble constant, the present-day expansion rate, deduced not from the rushing of galaxies directly, but from the memory of early acoustic waves. A spectral index that says the primordial fluctuations had a tilt, slightly favoring larger structures over smaller ones at birth. An optical depth that speaks softly of early stars reheating the universe and letting light scatter again, leaving a faint signature on large angular scales. Each parameter comes with uncertainties, always quoted, always respected. The gentle rhythm continues as Markov chains wander carefully through parameter space, guided by likelihoods shaped by the data and by the chosen models, converging slowly until the result is not a single number, but a small family of numbers nestled around a best estimate. The search for B-modes is a story of gentle perseverance. To see them, you must know the polarization angle well, and the leakage from temperature into polarization must be kept low through both design and data processing. Half-wave plates spin, sometimes continuously, sometimes stepping, modulating the polarization signal so that it moves to a frequency range where the noise is more benign. Pairs of detectors are different to cancel common modes, and the scanning is planned to crisscross each pixel at multiple angles. Lenses and mirrors are polished, and filters cut away the parts of the spectrum where the atmosphere or foregrounds would sing too loudly. A field is chosen in the southern sky, where the Milky Way's dust is a dim curtain rather than a bright tapestry. The gentle rhythm continues as the team reads the data from a season, reduces it, and sees a faint curl, checks it against maps of dust emission, and then checks again. The world is patient here. Nothing is rushed to a press release. The sky is the same today as it will be tomorrow, so the moves forward at the rate of confidence. The Sunyaev-Zeldovich effects enter softly from the side. Galaxy clusters are reservoirs of hot electrons, and when photons of the cosmic background pass through those clusters, some of them are gently shifted in energy. The resulting signal is a small distortion in the spectrum of the CMB toward clusters, a gentle dip at some frequencies and a lift at others. With enough sensitivity and resolution, a special map of clusters can be made by looking for this spectral fingerprint and counting clusters as a function of mass, and redshift becomes a way to learn about the growth of structure and the pressure of dark energy over time. There is also a smaller effect from the motion of clusters, a subtler shift caused by peculiar velocities, nicknamed kinetic SZ. These techniques rely on high-resolution telescopes placed in dry places, scanning and scanning, making maps that are deep enough to reveal tens of thousands of clusters, each a small dent in the smooth CMB fabric. The gentle rhythm continues as catalogues are compiled, confirmed with optical and X-ray data, and turned into constraints that gently narrow the possible histories the universe might have had. Lensing reconstruction is another whisper within a whisper. The path of each CMB photon is bent by the gravitational fields it passes on its way to us, an effect that gently blurs and remixes the original pattern. By studying the statistical properties of the map, especially the way different Fourier modes couple, one can reconstruct a map of the projected mass between us and the last scattering surface. This lensing map is like a soft fingerprint of all the matter, luminous and dark, that the light has encountered. Cross-correlating this map with galaxy surveys, or with maps of the cosmic infrared background, reveals a harmony among surveys, each one humming a part of a larger song. The gentle rhythm continues. There are many voices in this choir of measurements. Balloons rise into calm stratospheric winds and hold their position over Antarctica for days, sometimes weeks, floating above most of the atmosphere. The gondola holding the telescope swings only gently, and the sky, stretched out under the balloon's slow drift, becomes a polite parade of targets. Companies and agencies watch the weather, coordinate recovery, and the team waits with quiet nerves, then celebrates in a tone that respects the silence of the ice. The instruments up there feel the sun even more strongly, and thermal designs are tested in chambers that reproduce the long, thin cold of high altitude. The gentle rhythm continues as the flight returns, and crates are opened with careful hands, detectors and electronics removed and placed on benches where they will be read, and then read again. From space, instruments have the luxury of a view free from atmospheric flicker. In the deep cold of space, with the sun kept at bay by baffles and shields, a satellite rotates slowly, letting its beams trace great circles. The data come down in a stream that is steady and long. The sky is surveyed many times, in many colors, at a resolution set by mirrors and horns that were polished and assembled long ago. The pattern of scans is designed to cover the sky evenly, to allow the removal of drifts and to separate true sky features from instrumental baselines. On the ground, in a building that feels like it is always at night, the watches over this process, and when the mission is complete, the archive becomes an heirloom, carefully documented, open for others to use in years to come. The gentle rhythm continues as the community returns to these data, reprocessing with new methods, cross-checking with new maps, finding the same results with small refinements that tighten confidence. Imagine the hum of servers in a data center, the aisles cool, the lights dim, the sound a standing wave of gentle wind. On the screens, code scrolls by in pale colors. Version control system hold every change to every file, so that if a number shifts suddenly, the cause can be found. The pipeline is defined by names and by promise, each step with inputs and outputs that are both shaped and checked. At the end of a run, plots appear, and they are not fireworks, but familiar shapes with whispering variations that say the night was kind. Sometimes a run fails, not with a surprise, but with a quiet error message that a human understands. The error is fixed, the run restarts, and the gentle rhythm returns. Documentation is written in calm sentences that begin with words like first and next and then, and finish with a note about the figure that this piece of the pipeline produces. The people who write this documentation know that others will inherit the code, and they want those future hands to feel held. Calibration is a tender ritual. The dipole signal, caused by our motion through the universe, is a bright, simple yardstick, a global pattern that is well understood and always present. The instrument temperature scale can be pegged to that pattern, and small corrections applied so that a half-degree ripple is measured correctly in millionths of a degree. Planet observations add another anchor, their brightness known across frequencies. The beam is measured again and again, slightly different each time, because the environment and the instrument move and breathe. Gain variations are tracked, and if a detector's sensitivity drifts over the night, the drift is found and removed, with uncertainties recorded. The gentle rhythm continues as calibrator sources in the sky are visited like old neighbors. Tau A, the Crab Nebula, is a favorite for polarization angle. Its emission has a stable orientation, and by aligning the instrument's measurement with this known direction, the polarization angle can be set with care. The crab is not a crab here, only a faint steady compass. Time interleaves with this slow work. A sunrise at the South Pole is not a bright event, but a long, graceful gradient over days. In the desert, a moonrise can cast shadows that look crisp and forgiving. People come on shift with quiet greetings, and those off shift step gently past, their minds still half on the data they have left in the hands of co-workers. The food is simple, and the coffee or tea is poured into mugs that have a familiar weight. Notebooks accumulate calm notes that look like music to those who understand the language. A typical entry might say that scan 1732 drifted slightly at the end, that a filter warmed by a small amount during the third hour, that a patch of sky was masked due to a bright source, that the noise spectrum remained 1/f to a frequency that was acceptable. The gentle rhythm continues as the object of the work remains unchanged and unchanging, a sky that will wait encyclopedia. It contains tiny imprints of our motion, a global dipole that shows the solar system moving with respect to the average rest frame of the cosmos. It contains the sharp outlines of galaxies that glow in the microwave and sub-millimeter, their dust shining in a way that increases toward higher frequencies. It contains the patterns of our own galaxy's dust and electrons, sometimes bright, sometimes faint, forming a beautiful, complicated veil. It contains the small blurring effect of lensing, which can be undone, in part, to reveal a cleaner version of the primordial pattern. It contains the slightly darker and brighter spots that came from those early acoustic oscillations, preserved through eons of expansion, like ripples frozen in ice. The gentle rhythm continues as you let your eyes move over this map slowly, choosing to focus on a single area or to let your gaze drift. From these maps, the science reaches outward. If you remove the dipole, clean the galaxy's foregrounds, and smooth over the tiniest scales where instrument noise is most insistent, you can extract a set of values that describe the whole observable universe. This is the quiet miracle of cosmology. The universe is large beyond easy imagining, but its earliest light, processed through slopes and peaks in a power spectrum, can be summarized in a handful of numbers. These numbers are not everything, but they are a sturdy frame. The gentle rhythm continues as you imagine those numbers written in a calm hand on a whiteboard, next to a drawing of a flat universe, a diagram of the last scattering surface, and a timeline that stretches from hot to cool, from opaque to transparent, from plasma to neutral gas, to a rayonized medium filled with the first stars. The rayonization story is another soft layer. After recombination, the universe became neutral and dark, invisible light. The first stars took a long time to form, much longer than the gap between ticking of seconds to you now. When they ignited, their light began to rayonize the hydrogen around them, allowing photons to scatter again. This late scattering adds a gentle fuzz at large angular scales in the polarization pattern, and by measuring this, one can estimate the integral of electron density back through time, summarized in a parameter called optical depth. This information folds back into the interpretation of the spectrum, affecting how the amplitude of primordial fluctuations is translated from observed to original. The gentle rhythm continues as you picture the universe slowly lighting up, not as a sudden blaze, but as a million soft candles in fog. Null tests are a comfort. They are ways of cutting the data in half, or in four, or into odd and even scans, or into rising and setting observations, and checking that the differences look like noise and not like signal. If a feature appears in every half and remains when the data are shuffled, it likely belongs to the sky. If it disappears in differences, it is likely to be a slow, gentle drift or a glitch that needs attention. The gentle rhythm continues as plots of differences show flat lines with small random wiggles, giving a feeling of reassurance that the full map is trustworthy. Cross correlations between independent experiments add a deeper reassurance. When two teams with different instruments, different scanning strategies, and different analysis geometry of pointing. The telescope must know where it is gazing to high accuracy, and this is ensured with star cameras, gyroscopes, and careful mechanical models. The star camera sees the night sky, and by matching star patterns to a catalogue, it knows precisely where it is looking. The gyroscopes offer smooth guidance between star camera updates. The telescope's flexure under gravity as it moves is modelled calmly and corrected. The gentle rhythm continues as the pointing solution is verified by scanning bright and known sources and confirming that they fall on expected pixels. In a lab before deployment, the same care appears in optical benches and alignment lasers, in the feel of a lens sitting just right. Instruments feel weather, even in their quiet ways. Humidity changes the microwave opacity of the air. Wind can move something slightly, or make a feature that must be masked. Temperature can drift, affecting the gain of detectors. These effects are learned slowly and corrected calmly, with field seasons stretching long enough to capture the full range of the environment. The gentle rhythm continues as the yearly cycles of dry and wet, of cold and warm, are written into the calibration and become part of the way the instrument hears the sky. The custodians of data include archivists of a sort, people who make sure that after the observing and the analysis, the maps and their uncertainties are presented in a way that others can use. Files are placed in repositories with metadata that fully describe what is inside. Papers are written with appendices that detail choices and tests, acknowledged limitations, and future plans. The gentle rhythm continues as the field builds on these results, planning new instruments that will see smaller features, measure polarization more cleanly, and trace lensing with more fidelity. Imagine for a moment the early universe itself, not a violent vision, but a smooth, glowing fog, thick and bright, expanding evenly in all directions. Inside that fog, tiny ripples in density were present, like soft hills and valleys too gentle to touch, but real enough to guide matter slowly toward them. The fog cooled, protons captured electrons, photons moved freely, and what had been a glare became a diffuse, nearly uniform radiance. That radiance is still here, filling every room you have ever been in, your childhood bedroom, a winter train car, a summer night on a porch with moths tapping a lamp. The gentle rhythm continues as you realize the innocuous daring of this idea. The background glow you cannot feel still carries the fingerprint of a time so ancient that almost nothing else reaches us from then. Instruments that measure it often use bolometers, tiny devices that sense the energy of incoming radiation as a small change in temperature. These bolometers are held at a fraction of a degree above absolute zero, sometimes as low as a few hundredths of a degree, so that even tiny absorbed energies can be noticed. Another class of instruments uses amplifiers, low noise devices that take a small signal and make it larger without adding much noise of their own. Waveguides and feed horns guide the microwaves into detectors with minimal loss, and filters made from meshes and dielectrics shape the bandpass, allowing in measured with sources whose brightness is known. Engineers and scientists move calmly through diagrams that look simple only because 1,000 details have been distilled into a few neat lines. Component separation, the craft of peeling the CMB from the layered foregrounds, is an art that blends mathematics with caution. One method sets up a model for each component's frequency behavior and fits those models pixel by pixel, using the many frequency maps to constrain the unknown parameters. Another method constructs a weighted sum of the maps that minimizes variance while preserving the CMB spectrum, choosing weights that downplay frequency channels dominated by noise or foregrounds. A third uses Bayesian inference to combine prior knowledge of the components with the data, yielding maps and uncertainties that respect both the observations and the reasonable expectations for smoothness and physical plausibility. The gentle rhythm continues as the results are compared, and when the different approaches converge on the same patterns, a shared sigh of relief is felt across the collaboration. The concept of cosmic variance is a quaint sort of comfort. It says that because we see only one sky, not an ensemble of universes, there is a fundamental limit to how well we can measure some quantities. On the larger scales, where there are fewer independent patches to average over, the uncertainty is larger, and this cannot be reduced by building bigger telescopes or observing longer. It can only be reduced by having more universes to measure, which is not an option we have. This is not a failure, but a reminder of the calm boundaries of knowledge. The gentle rhythm continues as you accept that there is a built-in softness to our understanding, a blur that is part of the fabric of the reality we get to witness. Map-making algorithms carry names that feel like characters in a quiet tale. There are generalized least squares solvers that take into account the noise properties of the detectors, especially the tendency of some devices to have more noise at lower frequencies, the so-called 1/f noise. There are destriping methods that model this noise as a series of baseline offsets and solve for them so that stripes are not drawn across the final map by slow drifts. There are maximum likelihood methods that carefully consider the covariance among pixels, seeking the map that best fits the time streams given all known features of the instrument and sky. The gentle rhythm continues as these methods run on shared clusters, their jobs scheduled and queued, their memory carefully allocated. Pixelization on the sphere is a small, precise craft. One common scheme divides the sphere into equal area pixels that nest neatly when resolution changes, allowing maps to be compared and combined without fuss. Each pixel has neighbors that are known, and to compute derivatives or to smooth the map with a beam, you need only look around a small ring of these neighbors. The gentle rhythm continues as spherical harmonics are used to move between map space and harmonic space, each function a smooth pattern over the sphere, and the mathematics arranged so that the whole sky can be described as a weighted sum of these patterns. The weights are the power spectrum, and their estimation is done with care when the sky is partially masked, using corrections that have been derived and tested. Gravitational lensing, when reconstructed from the CMB, allows a lensing convergence map, a picture of how much mass lies along each line of sight. This map is a muted portrait of the universe between us and the last scattering surface, the cosmic intermediate years. By correlating this map with maps of galaxies, one learns how galaxies trace mass, how light connects to dark. By correlating it with maps of the cosmic infrared background, which trace star formation, one learns about the relationship between star formation and mass over time. The gentle rhythm continues as these cross-correlations are turned into constraints on parameters that describe how structure grew, how the universe's expansion slowed and then sped up, and how the subtle tug-of-war between matter and dark energy played out. Team culture in these projects is built on gentle habits. Meetings are scheduled with time for everyone to speak, but with no pressure to do so. Notes are shared promptly. A culture of internal review ensures that analyses are examined by people who were not the ones to write them, making room for fresh eyes to catch quiet mistakes. Reproducibility is a value here, and anyone running the pipeline should be able to recover the published results by following documented steps. The gentle rhythm continues as students learn from mentors, taking on small parts of the project, then larger ones, their confidence growing like dawn. Your breath remains slow and even. Imagine yourself filling a page with small squares, each square a pixel with a value that diverges from the mean by a tiny amount. In one corner, a slightly warm patch. In another, a slightly cool one. You are not rushed to finish because the map is patient. When you finish, you look at the whole and see that the differences are not random after all, but have a pattern that is more easily felt than defined, a feeling of scale that repeats. The gentle rhythm continues as you realize that this feeling is encoded in numbers, and those numbers encapsulate a history of oscillations in a plasma that filled everything, a calm memory of sound before stars. The hardware demands an embrace of slowness. Cryogenic stages cool down, not instantly, but over days, and then they stay that way if left alone, like a deep lake that never freezes at the surface because it does not need to. Heat straps are tightened. Thermometers are read in seconds and minutes, not in microseconds. The smallest mechanical distortions can matter for beams and focus, so the structures are stout but not excessive. The gentle rhythm continues as warmer stages radiate their heat into colder ones through careful shields, each stage nested like a set of calm bowls inside a cabinet that never slams. The way an instrument is tuned before observations begin has the feel of a gentle instrument being tuned before a concert. Biases on detectors are set to sweet spots where non-linearity is minimized and sensitivity is maximized, and small tests confirm that the responses are stable. The readout chain is checked for microphonic pickup, the tiny vibrations that can be introduced by wires or moving parts. Baffling and blackening are checked so that stray light does not bounce and find its way to places it does not belong. The gentle rhythm continues as sunrise comes. The doors close, the telescope moves to its nighttime posture, and the world becomes again very simple. The sky, the receiver, the data stream, the logs. There is something soothing about the sheer scale of these surveys. The sky is divided into with small dots after each good night, the pattern forming a constellation of its own. Beyond the microwave background, other whispers join. Hydrogen's 21-centimeter line offers a way to listen to the universe when it was still mostly dark, before the first stars had fully lit the cosmic dawn. Arrays of antennas spread across deserts and quiet radio reserves listen for this faint line, trying to see the gentle fall and rise of absorption and emission against the bright, smooth background. Terrestrial radio interference is a loud, unruly neighbour, and so a great effort is made to find quiet places, to filter and flag contaminated data, to build cabins that leak no radio waves. The gentle rhythm continues as these arrays slowly collect the power spectrum of 21-centimeter fluctuations, hoping to add another layer to the story told by the microwave background. Baryon acoustic oscillations, the fossil record of the same early sound waves, appear later in galaxy clustering. Surveyors map galaxies by the millions, and when their positions are analyzed statistically, a small preference for separation at a particular scale appears, the same wavelength that was set when the universe became transparent. This preference becomes a standard ruler, a way to measure the expansion history of the universe by comparing angular and redshift scales at different epochs. The gentle rhythm continues as charts of distance versus redshift are drawn, and when combined with CMB results, the synergy is nourishing and steady, letting the expansion history be pinned down more firmly. Returning to polarization, the E and B decomposition is an elegant act. The polarization pattern on the sky can be rewritten as two fields, one that has no curl and one that has no divergence. This separation is not just a mathematical trick, it reflects different physical origins. E-modes are the more abundant, produced by scalar perturbations, the same density variations that made the temperature fluctuations. B-modes require either gravitational waves from inflation or the lensing conversion of E into B by the uneven mass distribution. The gentle rhythm continues as maps are filtered to highlight these patterns, and as lensing B modes are measured and then removed in a process called delensing, allowing any leftover primordial B modes to emerge more clearly. Little details accumulate and matter. The absolute zero level of a map is not always obvious, and can be anchored by comparing to maps of known absolute calibration, or by requiring that the average of a clean patch of sky matches expectations. Polarization leakage from bandpass mismatch can arise when detectors sensitive to different polarizations have slightly different frequency responses, and if the foregrounds have different spectral shapes, intensity can leak into polarization. This effect can be modeled and corrected. The gentle rhythm continues as these small demons are found and tamed through repeated tests and careful modeling. You might think of the people again, because this is also a story of patience lived by humans. There is a person who loves seeing the uniformity of the noise spectrum when a new configuration is turned on. person who enjoys the slow puzzle of identifying a small artifact and following it back through the pipeline to its source, like a botanist tracking a water stain to a small leaky pipe that is easy to fix. There is a person who feels a quiet joy when a map from 2 different seasons aligns perfectly after calibration, sliding into place like sheets of paper aligned by a steady hand. The gentle rhythm continues as these small joys accumulate and keep a long project lively without excitement. The notion of likelihood is another soft idea. It is a mathematical way to say how probable the data are, given a set of parameters. It is the compass that guides the Markov chains in parameter estimation. Priors constrain what is allowed, gently biasing the result toward what is already known or reasonably believed. As the chains wander, they spend more time where the likelihood is higher and less where it is lower. Convergence diagnostics tell when the wandering has settled into a reliable picture. The gentle rhythm continues as histograms of parameters shrink and consolidate around their final forms. Computers today are fast, but the work remains shaped by time. Simulations run overnight, and in the morning, a set of files appears that shows how an algorithm behaves over hundreds of noisy realizations. Sometimes the result is exactly as expected, and the day is calm. Sometimes a small bias appears, and the team spends a week tracing it, finding that a certain filter introduced a phase shift that was not accounted for, or that a mask with a sharp edge introduced ringing that could be softened with an apodization window. The gentle rhythm continues as fixes are implemented and retested, with each change recorded and explained. Transparency with the public is part of the rhythm too. Data releases include not only the maps, but also the beams, the masks, the transfer functions, the noise levels, and simulation sets. Explanatory supplements walk through the pipeline with care, giving enough detail for others to replicate, or at least to understand the choices. Conferences and talks present results with figures that are clean and modest. The gentle rhythm continues as collaboration members take turns speaking, answering questions with honesty, and the phrase "we are still investigating" when that is the right phrase to use. There are test observations done before the main surveys begin. Small patches scanned to verify that reconstruction of polarization is unbiased, that the noise behaves kindly, that cross-linking is adequate, and that the scanning matches the plan. There are end-of-season summaries that tally up hours on sky effective depth and coverage. There are internal memos that note which hardware changes improved stability and which changes await implementation. The gentle rhythm continues as one season flows into the next, with hardware shipping back to laboratories for upgrades or staying in place for the next round. You might imagine yourself sitting on a low stool by a rack of electronics at 2 in the morning, the display showing temperature readouts and detector currents, the lights on the rack small and green. Outside, stars move quietly. You feel the comfort of knowing that most of the time, nothing happens quickly, and that this is a world where gradual change is the rule. You take a slow sip of water. A log entry is typed, the keys clicking softly, the words neat. The gentle rhythm continues as a colleague walks in, just odd. It might be from a cable that has worked itself slightly loose and is adding a slow oscillation to the data stream. The team reproduces the feature in lab conditions by gently tapping the cable, confirms the cause, secures the connector, and reobserves the field. The feature is gone. The gentle rhythm continues as the incident is recorded, a small lesson boxed and filed so that future teams can learn without needing to repeat it. The entire endeavor is not only about the past, but also about the future. New experiments are planned to see the polarization with enough sensitivity to find B modes from inflation, if they exist at levels accessible to us. This requires thousands to tens of thousands of detectors, carefully multiplexed to keep the readout both manageable and quiet. It requires meticulous control of polarization systematics, better calibration, better delensing. It requires sites as quiet as can be found, and better within band control of foregrounds. The gentle rhythm continues as design studies compare options for mirrors, for refractors, for hybrid systems, for scanning strategies under different site constraints. As we move more deeply into the survey era for all areas of astronomy, the CMB remains the calm backbone. It sets the initial conditions for structure formation, and as other surveys map galaxies, measure weak lensing at lower redshifts, and track supernova distances, the CMB sits at the high redshift end as a stable anchor. Joint analyses draw from the CMB priors and from the new data, combining them with care, ensuring that double counting is avoided, that covariance between datasets is included. The gentle rhythm continues as a coherent picture of the universe evolves, with tensions noted calmly when they appear and investigated without haste. In the grand scale of human culture, these surveys are one of the quiet ways we listen to the world beyond Earth. They are akin to listening to distant ocean sounds with hydrophones, or to low, slow seismic waves that move across continents, except that the instrument here listens to space-time itself, and to a light that carries news from when nothing had yet coalesced into stars. The gentle rhythm continues as you feel the smallness and the comfort of being a part of something that is both vast and peaceful. Still awake, comment the secret word, nebula. Rest now into another image. A clean room hums not with activity but with filtered air. Gowned figures move past tables where arrays of detectors are assembled. The arrays look like small pieces of jewelry, gold traces glinting under white light. The surface is matte and ordered. Under microscopes, bonds are checked, connections verified. Each array will be part of a focal plane, where each pixel is tuned to a particular band, perhaps 3 bands together, to allow spectral separation of foregrounds from CMB. The gentle rhythm continues as tests in a cryostat verify the responsivity, the noise equivalent power, and the stability of the readouts, and as the arrays are packed for their journey to the telescope, the narrative of foregrounds deepens in polarization. Dust grains align with the galactic magnetic field, and their across the sky. Synchrotron polarization arises with its own frequency dependence, generally stronger at lower frequencies. In patches of the sky used for B-mode searches, both are present at some level, and their spatial variation requires models that are flexible but stable. The gentle rhythm continues as templates are built, as priors on spectral indices are applied, and as the goal becomes not to remove the foregrounds perfectly, but to remove them well enough that the remaining uncertainty is smaller than the signal being pursued. Delensing is an act of refinement. The lensing B-modes are a known contaminant to the primordial B-mode search, but they can be predicted from maps of E-modes and from a map of the lensing potential, which can be obtained from the CMB itself or from external tracers like galaxies. By combining these, a predicted lensing B-mode map is built and then subtracted from the observed B-mode map, reducing the variance and allowing the primordial component to be more easily seen. The gentle rhythm continues as the fidelity of delensing improves with better E-mode maps and better lensing maps, pushing sensitivity to inflationary signals to lower levels. Phase switches, synchronous demodulation, and other readout techniques carry a similar calm elegance. By modulating the signal at a known frequency and then demodulating in software or hardware, the signal can be moved away from low-frequency noise drifts, reducing the impact of 1/f noise. This is analogous to rocking gently on a boat so that the slow sway of the water becomes less noticeable. The gentle rhythm continues as the choice of modulation frequency is made carefully, avoiding harmonics of mechanical vibrations and other known features. The atmosphere adds small, smooth structures to ground-based maps. On short timescales, it behaves like a slowly varying screen with structure on large angular scales. Filtering the time streams to remove long timescale variations can suppress this. Cross-linking the scans, scanning the same patch in different directions, allows map-making to reconstruct smaller scales while letting larger scales be sacrificed if needed. The gentle rhythm continues as the limitations of the site are acknowledged, and as the strengths of the instrument are matched with the scientific goals, focusing on the scales where the measurement will be cleanest. The art of beam characterization extends to the smallest details. The main lobe of the beam is often close to Gaussian, but the real beam has imperfections, small ellipticities, wakes from supports, diffraction features from edges. Side lobes can pick up ground emission, the moon or the sun, measurements over a wide area, sometimes using the moon or a strong source, allow the far side lobes to be mapped and either absorbed into the uncertainty budget or corrected. The gentle rhythm continues as a shadow of the telescope's surroundings is measured and understood, turning possible corruptions into known adjustments. When all is done, there is a release. The maps are posted, the spectra plotted, the cosmological parameters updated. Familiar figures appear, the gentle waves of the spectrum, dots with small error bars and theoretical lines passing smoothly through them. The plots do not surprise, they reassure. Papers cite earlier work and then become work that will be cited in turn. The gentle rhythm continues as the moves one decimal place tighter in a few parameters, opens a new window onto a phenomenon like delensing, and begins again to design the next iteration. Some nights are not clear, and those nights belong to tending and training. New students learn to run the pipeline on small data subsets. Old code is refactored quietly, made more readable. Documentation is updated, examples added. A small bug in a helper function that never mattered last year becomes relevant now because the data are deeper and it is found and fixed. The gentle rhythm continues as the weather clears in the forecast and the telescope is prepared to observe again. A cosmic neutrino background exists as well, another whisper, even fainter and harder to detect directly, but its presence alters the CMB through its effects on the expansion rate and on the pattern of fluctuations. The effective number of relativistic species, a parameter that captures this, can be constrained by precision measurements of the CMB and of large-scale structure. This is an indirect listen, a hand cupped not to the ear but to the air, feeling rather than hearing a small shift in pressure. The gentle rhythm continues as exotic ideas remain folded into ordinary measurements. In this vista, the human ear and the instrument's ear are mixed. We cannot hear microwaves, and yet when the detector current rises or falls in time with the telescope's motion across a source, the eye translates that into a felt sound. There is a rhythm in the scans, a beat at the scan frequency and at harmonics, and the power spectrum of the noise is like a music with a bass that must be low and smooth. The gentle rhythm continues as the mind plays with these metaphors and lets them fade again into the practical. Future missions dream of spectral distortions. While the CMB is a nearly perfect blackbody, very small departures from that perfection could have been introduced by energy injections in the early universe, by processes such as dissipation of small-scale perturbations or decays of particles. These distortions, labelled with Greek letters in textbooks, are subtle and require instruments that can measure not just brightness at a handful of frequencies, but the detailed spectrum across a wide range with exquisite precision. The gentle rhythm continues as design studies compare options for absolute spectrometers, for calibration schemes that hold the blackbody reference in a grip as gentle as it is firm. You drift to a lab bench with a thick top that keeps vibration low. On it sits a black box that holds a millikelvin refrigerator, a device that steps down from liquid helium temperatures to even colder levels with elegance, using quantum effects in helium mixtures to pump heat away. The system makes small noises, not loud ones, small gurgles and breath-like whooshes. A gloved hand reaches in, checks a connector, closes a lid. The gentle rhythm continues as a test tone is run through the system, the response recorded, and the line on the screen looks exactly as it did last week. An old friend returning with the same expression. The simplicity of the CMB spectrum is a calming thing, a nearly perfect Planck spectrum at a temperature just under 3 Kelvin, corrected for the dipole that comes from our motion, enriched by the tiniest anisotropies cosmologists, you hear understatement. They speak of significant detection with modest joy. They refer to concordance models and small tensions. They say consistent with within a range. There is poetry in this restraint because the subject is so large that only quiet voices seem respectful enough to speak of it. The gentle rhythm continues as words like power spectrum, transfer function, and covariance take on the texture of familiar river stones, smooth from much handling. The sky itself might be described with soft textures. The largest scales are like dunes with gentle curves. Intermediate scales have a pebbled feel, pleasant and regular. The smallest scales, beyond where the primary anisotropies dominate, hold noise and point sources, a kind of grit that can be removed with filters or masked. The gentle rhythm continues as the right scales are emphasized for each piece of science, as when a person dials a knob to bring a preferred range into focus and to let the rest blur. Galactic masks are drawn with patience. Areas of bright emission are avoided, not because they are bad, but because the goal here is different from the goal of studying our own galaxy. Apodization smooths the edges of these masks so that sharp boundaries do not introduce artificial ringing in harmonic space. The gentle rhythm continues as masks for different frequencies and different purposes are layered and intersected, each tuned to the science goal like a lens for a specific focus. Even the way plots are made has a calm ethic. Colors are chosen to be gentle on tired eyes, often blue and red to indicate low and high, with desaturated midtones. Lines are thin but visible. Error bars are present and not shy. Axis labels are clear. Figure captions explain without drama. The gentle rhythm continues as these visual choices allow a mind in the late hours to see what is needed without effort. Large collaborations can be slow, but in a good way. Internal checks take time. Papers can be reviewed by internal committees who look for clarity, for sufficient evidence, for completeness. Drafts travel back and forth, not because of argument, but because a shallow valley of misunderstanding must be filled in. The gentle rhythm continues as the resulting paper is sturdy, and those who read it feel supported by the arguments. Take another soft breath. Imagine again the early universe's fog, this time as a warm mist in a room with cool floor tiles. You stand barefoot, and the tiles cradle your soles with a faint chill. The air is still. The mist begins to clear, not all at once, but with patience, revealing outlines that sharpen into rich details over great spans of time. The gentle rhythm continues as this metaphor settles and dissolves. On hardware tables, kits of screws and washers are laid out in small bins, each bin labeled, each containing exactly what is needed and not more. This is a choice as much as a necessity. Clutter is avoided because calm work thrives on space and order. The gentle rhythm continues as a person reaches for the correct washer without looking up from their thought. Noise modeling is a soothing intellectual practice. The noise power spectral density tells how the noise varies with frequency. It is a curve that may be flat over a long range and rise at low frequencies. It can be fitted with a simple model and then used to weight the time streams optimally in map making. The gentle rhythm continues as white noise levels are quoted per detector, and as the effective noise in the map is quoted in microkelvin arc minute, a unit that has become a friendly standard. Time constants in detectors matter. A detector does not respond instantaneously to a change in incoming power. It has a small lag described by a time constant. This causes a slight smearing in time, translating to a small elongation in the scan direction on the map. Calibration of this effect and deconvolution in the time streams corrected. The gentle rhythm continues as small test signals determine the time constant and as residuals are checked for stability. Instrument polarization can be induced by the optics. Mirrors at non-normal incidence can introduce polarization that must be characterized and corrected. Lenses can have birefringence. The optical design is tested with polarized sources to map out these effects. The gentle rhythm continues as these systematics are characterized to levels below the signals of interest. Faint sources in the maps are catalogued. Some are dusty star-forming galaxies whose emission peaks in the far infrared. Some are active galactic nuclei with flat spectra that extend into the microwave. Their contributions to the power spectra can be modeled and subtracted or masked. The gentle rhythm continues as source counts are measured, and as they become an ancillary science in their own right, a piece of the cosmos's gentle murmur that has been heard along the way. When the day's work is done, someone might look up and notice a small, satisfying symmetry in the code base, the way a function for beam deconvolution mirrors a function for beam convolution used in simulations. These symmetries make maintenance easy. The gentle rhythm continues as the code ages gracefully, not with pietrot, but with careful pruning and growth. In teaching, a mentor might begin with a simple picture, speaking of a cosmic afterglow, and then gradually add layers, anisotropies, power spectra, polarization, lensing, foregrounds, and parameters. At each layer, the student nods and sees the shape of the whole more clearly. The gentle rhythm continues as the student asks a calm, precise question, and the mentor answers, sometimes saying, "Let us check," and returning the next day with a figure that clarifies the point. Sometimes the quiet is interrupted by a cosmic event that shows up in the data as a burst of unexpected signal. These are rare and carefully checked to see if they belong to the sky or to the instrument. Most are terrestrial or near-Earth artifacts, and they are gently flagged and set aside. The gentle rhythm continues with a steady confidence that the dominant story is the older, enduring one. The archives that store CMB data are built to last. Copies are kept in multiple places. Checksums ensure that files do not quietly corrupt. Metadata are stored in human-readable formats as well as in databases. The gentle rhythm continues as future researchers download maps and use them in ways not yet imagined, appreciating the care that kept the data alive. Philosophically, this is a universe is what it is, and our ability to measure it grows with our tools and our patience. In the end, the CMB tells us that our universe is old and flat and filled mostly with things we do not see directly, like dark matter and dark energy. It tells us that the seeds of structure were laid down in a way consistent with a simple, elegant early process, one we call inflation. And it tells us by our limited ability to see the largest scales with high precision that there is a kind of built-in uncertainty to which we must bow. The gentle rhythm continues as we accept these truths and find them comforting. Outside the lab, the world is slow. A quiet road leads away. Grass blades bend and lift in a breeze. A sliver of moon sets early. Then the stars take their calm, long turn. The telescope stands, an ear to the sky. The gentle rhythm continues as the instrument does what it was made to do, and as the people who built it let it be while they rest. Beyond the CMB, gravitational waves in the nanohertz range are sought by timing arrays of pulsars, listening for a background that is like a murmuring sea. These two map an ancient whisper, not of light, but of the stretching and compressing of space. The universe offers many registers, and each one rewards patient listening. The gentle rhythm continues as you hold in your mind the image of a shared practice, many communities listening together to different aspects of the same grand quiet. Astronomy has always been about light that left long ago. The CMB is the oldest light we can see directly. Mapping it is an exercise in making the most of a finite, gentle resource, a sky that is the same for all of us. That sameness is a comfort. It means that despite the differences in our nights and the places we stand, the sky above us shares a foundation. The gentle rhythm continues as you feel your breath flowing like a quiet tide, in and out, in and out. Close your eyes if they are not already closed. The universe's whisper is steady and soft. The instruments that listen are patient and calm. The people who tend them are careful and kind. The data that emerge are often beautiful, sometimes surprising, and always honest about their limits. The gentle rhythm continues as you imagine the slow turning of a spacecraft, the slower drift of a balloon, the slower yet pivot of a mountaintop telescope surveying a stripe of sky for the 100th time and the 1000th time. There is room in this story for wonder and for gentle curiosity. If your thoughts wander, let them. If you drift away, the story will still be here when you return. The cosmic microwave background does not hurry you. It has been here for billions of years and will be here tomorrow. The gentle rhythm continues as you consider that fact and find it restful. You might imagine a single photon, born in the last scattering surface, travelling long after the fog cleared, weaving through the slight gravitational dips and rises, altered in its path but not in its origin story, arriving at your instrument after a journey so long that the photon has known no other destination than an atom in a detector that will turn its arrival into a tiny electrical change. The gentle rhythm continues as this image becomes simple and comforting, a single step in a chain that crosses time chin and feel safe under it. The universe has made a cover that fits everyone. The gentle rhythm continues as the night stretches out and carries you. As you rest here, remember that the next quiet video can begin automatically from the playlist if you like, nudging you deeper into sleep while the learning continues softly in the background. If you have not already, a like and a subscribe help us keep releasing these calm explorations often, and they gently tell the algorithm to bring you back to this safe, sleepy space. For now, feel the present room cradle you, feel the bed support you, and let your breath and the universe's whisper